Okay, good afternoon to all. So, this is our 10th lecture. In the previous lecture, we started our discussion on the fluids statics, and specifically we talked about the pressure distribution over a fluid element, which we found that it is uniform in all the directions. Okay, and then second one, we tried to estimate the forces because of the pressure, and then how basically pressure gradients varies with gravitational field. So if you recall, last we have stopped at this point that del P by del Z is equal to minus of rho into G. Okay, so it clearly shows that there will be variation of pressure with the elevation, with the vertical direction, because if you recall, the Z direction we have assumed in this side, and G was acting in the negative direction. Okay, so now this is the interesting point that if we have any confined liquid or any confined fluid, in that actually in the horizontal direction pressure will be the same. Okay, but on contrary, in vertical direction only we will be having variation of the pressure. Okay, so now what we can see from this particular thing, that if I have say any randomly oriented structure, and in that structure if I want to measure the fluid pressure, so say this is some structure and it is filled with water, it is completely filled with water. Okay, but one portion of this is actually filled with some other fluid. So say here we have mercury, and this above we have water. Okay, so now you can clearly see that if I mark any points over here, say this is my 1 point, this is second point, this is third point, fourth point, fifth point. So these are the points A, B, C, D, E. Okay, so on these point, all these points are nothing but at the same elevation level. Okay, so if these points are at same elevation level, then you will be finding that pressure at A will be equal to pressure at B, C, D. What about pressure at E? Will it be same or will it be different? For
For a same liquid, it will be staying at the same elevation.
Yes.
The liquid is changing.
Here liquid is changing. Okay, so one important point you have to note it down, that when we are having continuous uniformly distributed liquid, then only we will be having the same pressure at the same height. Okay, so the important keyword is continuously uniformly distributed fluid. Okay, so here if you see between point D and E, if you start from point D, you can move through this path, then through this path, then up to this point you are having continuity. Okay, so through this particular point you are having continuity, but after that you are having discontinuity because same uniform distribution is not maintained. After that we have some other fluid over here. Okay, so that's why we are having actually not continuous distribution. So that is the reason that pressure at point E will be different than pressure at point ABC. So I can write pressure at A equal to B equal to C equal to D, but it is not equal to pressure at point E. Okay. Another important point is whenever we will be talking about the pressure, pressure will always be acting normal to the surface. Okay, so if I say at point A pressure will be acting in this direction, at point B pressure will be acting in this direction, at point C it will be acting in this direction, at point D it will be like this, and at point E it will be, has to be normal, so it will be like this. Okay, so this will be the pressure at point E. Okay, so now what we will be doing, if we see this previous discussion, so we have found that del P by del Z is equal to minus rho times G. Okay, so if I have to estimate the pressure at two different points, okay, so what we have to do, we have to integrate this equation. So when I will be integrating the equation, I have now two dependent variables over here. So one is rho and other one is G. So now we have to first estimate what is the distribution of density and G with the elevation. Okay, so if we talk about the gravity, then we know that gravity can be related G equal to G naught times R naught by R whole square. Okay, where R naught is nothing but radius of the earth surface, which is equal to 6400 meters, and then G naught is nothing but gravity at the surface, earth surface. So gravity at earth surface is 9.81, okay, meters per second square. Okay, so now if you vary R, okay, yes, sorry, 6400 kilometers. So what we have is G equal to G naught into R naught by R square. So here radius of the earth surface is 6400 kilometers and G naught, the gravity at the surface of the earth, is 9.81 meters per second square. Okay, so now if I consider the variation of R, okay, so if I consider that I am moving away from the surface of the earth, then you are finding that gravitational field is nothing but inversely proportional to R. So it means its value should decrease. Okay, so particularly when we discuss the concepts of fluid mechanics, at max we can consider the compressible flow situation where we are having, say, a supersonic fighter jet is moving in the atmosphere. Okay, so typically if you see the supersonic fighter jet, that will be moving at a distance of about 20 kilometers from the earth's surface. Okay, so it means at max, whenever you will be finding the interaction of that, if you have to find out R, then R will be 6420 kilometers. Okay, so if you consider this range, in this particular range you will be finding that difference between G and G naught is 0.06%. Okay, so this difference is very, very small. So typically whatever the fluid dynamic systems or the interactions of the fluid we will be doing in our atmospheric conditions, there we will be finding that there is not much variation in the values of gravity. Okay, so that is the reason that we can assume over here gravity as constant for this course of fluid mechanics. Is this point clear? Because we are dealing with the system where we will not be even moving away beyond 20 kilometers from the earth's surface, and even up to 20 kilometers also the variation of gravity from the surface level is actually 0.0. Okay, so that is the reason we can take this constant. Then comes the other parameter, which is nothing but density. So density, we all know that for gases it is a strong function of the pressure, but for and it will be significantly varying with elevation also. Okay, but for liquids, typically considering their incompressible nature, if the pressure change is not very much large, okay, too much significant pressure change is not there, then density can be assumed constant. Okay, so for liquids I can consider that typically in our normal operating range, if our pressure change is not significant, then I can consider that extremely significant. There can be significant, but it should not be extremely significant. Okay, so then I can consider liquid to be of constant density, and in this situation if I have to measure the pressure, then I am having minus rho g. So if I consider that, say I have a fluid and then this is my positive z direction, this is a liquid filled inside this container, this is the free surface where pressure is P naught or P atmospheric. Okay, and this is location Z1. If I want to measure pressure P at any location Z, then what I have to do, I have to integrate this particular equation. Okay, so while I will be integrating, it will be integral of one more important point, because now this gradient operator, yesterday we have seen that del p by del x is 0, del p by del y is 0. So this gradient is only existing in the z direction. So in place of del, I can write it as dp by dz. So in case of partial derivative, I can write the ordinary difference. Okay, because pressure is dependent on only a single variable z. Okay, so from here integral of dp from z1 to z will be equal to minus rho g is constant, integral of dz from z to, this will be from z1 to z, and integral of pressure will be from, because at z1 pressure is nothing but p naught, and at that point we are saying that pressure is p. Okay, so from this we will be finding that p minus p naught is equal to minus rho g times z minus z1, and ultimately pressure will be nothing but p naught minus rho g into z minus z1. Okay, so if you are measuring the z from the bottom side, then you will be finding your z1 is actually greater than z. If you are taking the reference at the bottom, corresponding to that, you will be finding your z1 is greater than z, and this negative negative will become positive. So ultimately your pressure P is greater than P naught. Is this point clear? So now with this you can answer one simple question. So in thermodynamics, when we talk about the mechanical equilibrium, we say that pressure at each and every location within the system should be same. Okay, then only we will be calling it as thermodynamic mechanical equilibrium. Okay, but if you talk about a container and this container is filled with water, so you will be finding here pressure is P naught. If you go below to some height, some depth H1, there your pressure will be P naught plus rho g H1. If you go to some other depth, say H2, then it will be P naught plus rho g H2. So here pressure at different elevations is actually different. So can we call this system in equilibrium? Can I say this is in mechanical equilibrium? Any answer? You might have already studied in thermodynamics now, mechanical equilibrium. Can we call this in equilibrium or not? No. Okay. So whatever the definition you have studied over there, based on that, you can say that it is not in equilibrium. But if you see, are you finding any disturbance over here? Is there any acceleration? Fluid is resting in the completely rest position. It is in the equilibrium position. It is not getting disturbed. Okay. So this system is in equilibrium. Now why it is in equilibrium? Because pressure at any point, okay, at any depth, whatever high magnitude of pressure is there, it is basically nothing but balancing the weight of the liquid which is over there. Okay, so that's why in this situation there is a balance in between the pressure and the weight. So that is the reason for existence of equilibrium in this situation. Okay, so what I am trying to say over here is that, say if I consider any control volume over here, okay, so in this control volume for this liquid element, you will be finding that from top some P1 pressure is acting, okay, and from bottom some P2 pressure is acting, and of course P2 has to be greater than P1. So that is the reason while I am drawing the arrow, I will draw this P2 little bit bigger arrow. So this is the larger arrow. Okay. Similarly from sides also there has to be pressure. So here pressure is P1, but on the bottom face pressure is P2. So from sides, if you see, these arrows will keep on increasing linearly. Okay. Similarly from this side also there will be there will be pressure acting. Now you can see on this fluid element, if you consider that h is height of the fluid element and a is its cross-sectional area, okay, then there will be some weight of the fluid element also acting in downward direction. So you will be finding that weight of fluid element, which is equal to rho times area into h into g, okay, that is acting in downward direction. That will be nothing but equal to P2 minus P1 times E. Is this one clear? Okay, and in the horizontal direction, if you see, in the horizontal direction gravity is not acting and pressure force is having actually similar profile from left face as well as from the right face. That's why these will cancel each other. Okay, so this is the reason that if I am having a liquid fluid in a container, though pressure at different locations along the height, okay, along the elevation, it is different, but still I can call the system to be in equilibrium, because pressure at every point, okay, is nothing but balancing the weight of the liquid above this. Okay, so if you take any point at h1 location, then pressure at this location, say P1, this is balancing the weight up to this height. Then if you take pressure P2, this is balancing the weight up to this height, and the bottommost surface is actually balancing the weight up to the total height. Okay, so that is the reason that pressure at different locations is balanced by the weight of the fluid element. Okay. Now we will talk about gases. So in case of liquids, we have obtained this equation that with elevation I can write pressure as nothing but P naught minus rho g times Z minus Z1. Okay, and if you measure the Z depth from the free surface, then you will be writing this sign in place of minus as positive. Is this one clear? Now, if we talk about gases, can you tell me what will be happening in case of gases? In case of gases, density will be changing significantly with the elevation. Okay, so density will not be constant. So typically, when we talk about the gases, we have to take some assumption in order to develop the relationship in between pressure and the density. Okay, so what we will be doing, one of the famous equation we all know is ideal gas equation, and for atmospheric air at normal conditions it can easily be applied. Okay, so if I write P equal to rho RT, then rho I will be getting as nothing but P by RT. Okay, so now if I substitute this into our main equation, which is dP by dz equal to minus rho times g, so I will be getting minus, in place of rho I will be writing P by RT into. Okay, now let us consider that our temperature is constant. So this is the isothermal assumption. Okay, with elevation temperature is not changing. This is the assumption I have made over here. So if I take this assumption, then I can write RT as constant. So I will be getting dP by P is equal to minus G by RT into dz. Okay, is this one clear? Now I can integrate this equation from P1 to P2 and this one from Z1 to Z2. So ultimately what you will be getting? You will be getting this dP by P will be ln of P2 by P1 equal to minus G by RT into Z2 minus. Okay, so this is the equation for pressure variation with elevation. If I consider my gas to be an ideal gas and I have nothing but the isothermal assumption. Okay, is this one clear? But in reality, if we see, particularly in the troposphere, which is most nearest to the Earth's surface, okay, in the troposphere, which is up to how much kilometers? 11 kilometers. Okay, we experience that temperature varies with elevation in a linear fashion. Okay, so as we move away from the surface of the Earth, the value of temperature decreases and it decreases in a linear fashion. Okay, so I can write that T equal to T naught minus beta Z, where T naught is the temperature at surface, Z is elevation, and beta is something which is called as lapse rate. And value of this lapse rate is 0.0065 Kelvin per meter. Okay, is this point clear? So for each meter rise in elevation, there is 0.0065 Kelvin decrease in the temperature. Okay. So now if we couple this equation to our previous relation, then we will be finding more accurate prediction of the variation of the pressure in the elevation or basis. Okay. So that is the reason now whenever I will be writing this equation of dP by P for gases, which is minus G by R T, in place of T now I will be substituting, it will be becoming minus G by R, and in place of T I will be writing T naught minus beta into Z. Is this point clear? And here I will be having nothing but dz. Okay. Kelvin per meter. K is Kelvin, capital K is Kelvin, and this is per meter. Okay. So when we write small km, then it is kilometer. Now what we have to do, we have to integrate this. So at the surface we have pressure as P atmospheric, and at any point Z distance away from the elevation I will be having pressure as P. At the surface our elevation will be 0, and at any point Z it will be say something. Okay, so these are the limits of integration I have put over here. Now if I see G by R is constant, okay, so G by R I can take out, and left side will become ln of P by P atmospheric equal to minus G by R ln of T naught minus beta Z upon T naught minus 0 times 1 by minus beta. Is this one clear? So from here I will be getting ln of P by PA can be written as ln of T naught minus beta Z by T naught whole power G by R beta. Okay, so ultimately I will be getting that P by P atmospheric is equal to 1 minus beta Z by T naught power G by R beta. So this is how pressure varies with elevation in troposphere. Okay, in different layers of the atmosphere, variation of temperature happens in a different fashion. So in some layers it remains constant, in some layers it increases, in some layers it decreases. So particularly we are interested in close to the Earth's surface. Okay, whenever we are moving out of that, that is not in the scope of this particular course. But if you want to get the detailed variation of temperature and pressure, how it varies in different layers of the atmosphere, so you can refer to your textbook FMY, where they have given the detailed curve for different layers of. Okay, is this point clear? So now we have got this variation of the pressure. So once we have this variation of the pressure, we have to also utilize these principles to measure pressure for different systems. If we have to measure the pressure, then what are the fundamental devices and how we can develop these devices based on our this understanding of variation of pressure in the elevation. Okay, so very fundamental device which was used in the history for measurement of the atmospheric pressure was barometer. Okay, so what is a barometer? Barometer is nothing but there is one big vessel which is filled with the liquid. Okay, so let us consider in this case it is filled with liquid mercury. Okay, so this is filled with liquid mercury and it is open to normal atmospheric conditions. So this is the free surface of the mercury. Now, if I fill a tube with mercury, so this tube is also filled with liquid mercury. Okay, and after that what I will do, I will invert this tube in here, this container. Okay, so I will place now this tube something like this in the container, and now you will be finding that here I will be having some rise of liquid level within this. Okay, so what is the reason for this rise? Say it is rising up to this height. This is height h. So now you can see this is open to atmosphere. So here pressure acting will be P at atm. Okay. Now from this point to this point, if any point I am considering at the same height level within the tube, so it is also continuous and uniformly distributed liquid. So at this point also my pressure will be P atm. And what will be the pressure in this inverted portion of the tube? In this inverted portion of the tube, we will be having nothing but the vapor of mercury. Okay, so only thing it can exist over here is nothing but the vapor of mercury. Okay, so vapor of mercury is having, so if I consider this at the normal atmospheric conditions like 27 degrees Celsius temperature, so corresponding to this temperature, the vapor pressure of mercury is 0.002 millimeters of mercury. So value of its vapor pressure is nothing but 0.002 millimeters. So vapor pressure of mercury is actually negligible. I can assume this to be 0. So if it is 0, it means from here I don't have any pressure, but from bottom side I have this P atmospheric pressure. So this P atmospheric pressure is nothing but balancing the weight of this liquid which is staying inside this tube. Okay, so weight of liquid staying in the tube will be on per unit area basis, it will be rho GH. Is this one clear? So this equation when I have written it is on per unit area basis, because if you have to write the force, then you have to write P atmosphere into area and rho AH is the mass into G. So AA will be cancelled. Okay, so this is how we can actually measure the atmospheric pressure using a very simple device. So this particular device is called as nothing but a barometer. Okay, so when we are using the barometer, we have to keep some consideration into mind. First is the diameter of the tube should be greater than 1 centimeter. Okay, if diameter of tube is less than 1 centimeter, then there can be capillary rise or fall. Okay, so if I am considering any diameter less than 1 centimeter, then what I have to do? I have to use a correction factor of capillary rise or fall into the estimation of H. Okay. Another important point is whenever we are talking about this fluid, so we are not having any consideration of area over here. Okay. So the only thing I have to keep diameter of the tube greater than 1 centimeter, but greater than 1 centimeter, then there is no limit. I can keep any tube. Okay, because it is supported by the pressure from the bottom. So in place of this diameter, I may have also a tube of some larger diameter like this, but here also I will be finding the rise in water level is actually up to the same height. Okay, so there is no height difference in rise of the water level. Okay, so typically under the atmospheric pressure condition, you will be, can you tell me how much will be the rise in mercury level over here? 760. So at normal atmospheric pressure in terms of mm of mercury is 760 mm of Hg. Now this point will explain you why we go for mercury in barometers. If I convert this height into the equivalent height in terms of water, then how much it will be? So if you convert this into equivalent of water, you will be finding the height is 10.3 meters of water. Okay, so in terms of water, this height is how much? 10.3 meters. So it means that if you use water for your barometer, then you need a tube of more than 10.3 meters, then only you will be able to find out. So you can clearly see the reason for choosing mercury for different pressure measurement devices. Have you gone to doctor for getting your blood pressure checked? Any one of you? Maybe not at this age. Okay, so if you go to doctor, what they are having? They open something and then they try to, and then they read the label. So the fluid inside that tube is nothing but mercury. Okay. So what I have done actually, let me see, I have ordered two blood pressure machines. So I will try to show you how to check the blood pressure. Okay, so maybe these are not yet delivered. Delivery date is around 9th of September. After that I will show you. Okay, so you can check your blood pressure by your own. Okay, so this is barometer. Then another important device which is based on this principle, that is called as manometer. Okay. So can you tell me what is a manometer and for what purpose it is used? Anyone is having any idea? Have you not studied in thermodynamics? Okay, so manometer is a device which is used for measurement of the pressure of a system. Okay, now manometers comes in different configurations. It can be used to measure the pressure with reference to the atmospheric condition. It can be used to measure the pressure difference between the two systems. Okay, so there are many configurations of the manometer, but one simple configuration we can consider over here is, let us consider that I have a system and this contains some fluid of density rho and it is having pressure P1. Okay, so what I will do, I will connect this system to a U-tube. This is a U-shaped tube and the other end of this tube is open to atmospheric conditions. So here it is having nothing but P atm. Okay, now in this manometer we have to use some fluid. So let us consider I have used a fluid over here and this particular fluid is nothing but having density. This particular fluid is having density rho m. Okay, the fluid which we use inside a manometer, that is called as a manometric fluid. And density of manometric fluid is actually rho m. So typically what we do when we use the configuration of the manometer, we always keep density of this manometric fluid greater than the density of our fluid whose pressure actually we are trying to measure. Okay, the fluid which is contained in the system. Why we need to use this? Because if I am using this configuration of the manometer, then heavier fluid will be resting at the bottom and lighter fluid will be at the top because of the gravitational stratification. Okay. So because of this, whenever we use this type of U-tube manometer, always we have to consider density of manometric fluid to be higher than the density of the other fluids which we are using for measurement of the pressure. Okay. Then third important assumption is, whenever we are using a manometer, then always we have to consider dia to be greater than 1 centimeter, because if you use smaller dia, then capillary correction has to be taken. Okay. So now, with this configuration, if I simply consider the two branches of a U-tube manometer, and if I have manometric fluid filled inside this, and this is open, both sides are open to atmospheric pressure condition, will there be any difference of height between the two branches? So two branches will be at the same level, because here also P atmospheric pressure is acting, here also P atmospheric pressure is acting. Okay. Now you can see that one end is subjected to pressure P1 and other end is subjected to pressure P atmospheric. And let us consider P atmospheric pressure is less than P1. So if P atmospheric pressure is less than P1, it means now P1 pressure will push the fluid from its branch to the other side. Okay. So because of that, you can see the level is something like this. So this is the, on the left side I have up to this point, and in the right side say I have up to some height h. Okay. Now this P1, here also we are having some fluid. So basically in other portion of the tube this fluid is filled. So it is having density how much? Rho. Okay. And let us consider that the distance from this point to this point is nothing but A. Is this one clear? So now this horizontal level which I have considered over here, from this point to this point I have continuous uniformly distributed fluid. So as I have continuous uniformly distributed fluid, if I mark this as point A and this as point B, then I can simply say that pressure at point A will be equal to pressure at point B. Is this one clear? Pressure at point A will be equal to pressure at point B. Now pressure at point A is how much? P1 is the pressure over here, plus ρ1 is density of the fluid, and it is through height A. So ρ1 GA, and PV will be nothing but P atmospheric is the pressure acting from the top, plus ρm is density of the manometric fluid into GH. So I can say that P1 is nothing but P ATM plus ρm GH plus ρ1 G. Okay. Now if I consider that my fluid which is filled inside this container, this is nothing but a gas. So for gaseous fluid its density will be very small in comparison to manometric fluid. So I can neglect this term ρ1 GA, I can approximate it nearly equal to 0. So from here I will be finding that P1 is nothing but equal to P atmospheric plus ρm. Okay. So this pressure, when I am adding the atmospheric pressure over here in the right hand side, so whatever the value of P1 I am getting, this is nothing but in absolute scale. But if I have to find this pressure in the gauge scale, then I will be getting P1 as simply equal to ρm GH. So this is my value of pressure in gauge scale. Okay, so I already explained to you yesterday that gauge scale and absolute scale both are important, but which one we have to use, that depends upon the requirements. Okay. Now another variant of this manometer which we can use to estimate the pressure difference between the two systems, that is called as a differential manometer. Okay, so what do we mean by differential manometer? Like say here I am having some system having pressure P1 and density of fluid as rho 1. Okay, and in the other side I have some other system having pressure P2 and density rho 2. Okay, so for this type of configuration, if my manometric fluid is say something like this, so here it is having say height h, this height here is a1 and this height here is a2. So now can you tell me how I can calculate the pressure difference P1 minus P2? This is something which I want to estimate. Please tell me how I can estimate this. Say this is my point A, this is my point B. Once again pressure at A will be equal to pressure at B. What is the value of pressure at A? P1 plus rho 1 G A1 plus rho n G H, that will be equal to rho 2 G. So from here I can simply find out the value of P1 minus P2 or P2 minus P1. So here which one is larger? P2 is larger. So here P2 is greater than P1 as per this configuration which is. Okay. Now let me give you one more.
The height difference between the system doesn't matter anything on the which one is higher.
Yes, why it is not mattering? Because inside the closed vessel it is already having pressure P2 which we are considering. Understood? So now if I consider that I have some manometer, very complicated arrangement, something like this. I will not draw the double line system but simple line diagram I will show. P1 rho 1, P2 rho 2, okay, and say one level I am having at these 2 points A and B, and height is up to h distance. So up to this distance I will be having manometric fluid, okay. Then another level I am having at this point, so this is a C and this is D. And then third level I am having this point, so this is height h1, this is height h2, and say manometric fluid is rho m2, and then here it is rising up to height h3 as rho m3, and after this point say I have this density rho 2 up to height a2, and this is up to height a1. You have to find out P2 minus P1. Can you tell me how we can do this? How to find out P2 minus P1? Please tell me how to find out P2 minus P1. P2 minus P1 I can write as P1 plus or in other sense P1 minus PA plus PA minus PB plus PB minus plus PC minus PD PD minus PE. What I will get out of this? Out of this equation I will get nothing but P1 minus P2. So let me write left hand right side also. Is this point clear? Now tell me, what is P1 minus PA? P1 is here, PA is at this point. So P1 minus PA is nothing but minus rho 1 G A1. Can you tell me why I have put negative sign over here? Because PA will be greater than P1. Okay. Then A and B is cancelling out directly. What is the difference of pressure between B and C? What is PB minus PC? Plus rho m G H1, because PB is greater than PC. Okay. Then CD will be cancelling out directly. What about PD minus PE? Minus or plus? Minus rho M2 G H2. Then E and F will be cancelling out. F and 2 plus rho M3 G H3 plus rho 2 G A. Okay, so this is the equation. So I have drawn a complicated configuration, but out of this our equation is very simple. That is simply based on the pressure at different elevations. Okay. So this type of complicated configuration is not used in practical situations. This is just for testing your analytical. Okay. Then another variant of the manometer, which is also very popular, that is called as inclined manometer. Okay. So typically inclined manometers are used in the situations where we have to increase the sensitivity of the system. Okay. So for example, if I want to have more sensitive system, what is the meaning of sensitivity? For unit change in pressure, how much is deflection in the level height? Yes. So that is nothing but sensitivity of the manometer. Okay. So if we are dealing with the system where variation of pressure is very, very small and you want to record these small variations in the pressure, then you need a more sensitive system. Okay. So in vertical direction we cannot do anything because this is constrained by gravity. It will be moving only specific distance. Okay. So what we want to do, we want to improve that. So for that purpose, what we can use this inclined orientation. So here one branch is straight but other branch is inclined. Say it is inclined at an angle theta. Okay. Now if I have the manometric fluid level something like this. Okay. So this is my baseline. So you can see from baseline, this is the rise in height h. But if you see the marking you have done along the length of the tube, then say L is this one over here. So now you will be finding that this angle is theta. What is the relationship between h and L? H by L is nothing but, and L is equal to h by sine theta. If I take theta equal to 30 degrees, what I will be getting? If I take theta equal to 30 degrees, how much I will be getting? L equal to how many times of h? Sorry? 2h. Yes. So it means that for the same change of pressure, if in vertical direction your height is changing by h amount, for a manometric branch which is inclined at an angle of 30 degrees, it will be changing by, so sensitivity is increased. Okay. Now you will be having scaling on this inclined one. So inclined one you will be having actually more deflection in comparison to the vertical. Okay. So this type of manometers are employed when we are having more, as I already told you, when we are having the sensitive, we require more sensitivity. So that is, it means our system pressure is changing by very less amount. Okay. Now, one very important aspect of the fluid statics is that whenever we are building the dams, okay, so what dam is doing? The structure of the dam is actually holding significant amount of water behind it. Water is present in a water bottle. Okay, so that water walls of the water bottle are actually supporting the pressure which is acting on its surface because of the presence of the water. Okay, so we have to estimate how much force this pressure actually is acting on underwater systems so that we can design these underwater systems. If you have submarine, so submarine is subjected to the different structures of the outer body of submarine are subjected to actually pressure force from all the directions. So that determination of that pressure force is very important because it will be helping in structural design of these solid structures as well as in stability of the solids. Because if forces acting because of the fluid pressure are unbalanced, then these structures will be having chances of collapse. If structures are floating, then there will be chances of unstable behavior of that system. Okay. So typically, if I have a container which is filled with water, can you tell me what will be the force which is acting on the side of the container? Here pressure is P atmospheric. As I keep on increasing in downward direction, pressure will keep on linearly increasing. So I will be finding that, say, here my pressure profile is something like this. If other side of this container is subjected to atmospheric pressure condition only, then from other side I will be finding uniform pressure acting at each and every point. Okay. So what will be the net force acting on this structure? Say this is P ATM, so this will be also P ATM, and at this point pressure will be P ATM plus rho GH. Okay, so can you estimate the net force which is acting on this structure? This is a simple linear relationship. Okay, so this type of situation for complex submerged bodies we will try to actually analyze in our next lecture.